You know, usually when we think about a ticking clock in a quiet room, there's this really profound sense of comfort. It feels totally objective.
Right. It's rhythmic. It's dependable.
Exactly. It's rhythmic, the second hand moves, and, with just absolute certainty that a second has passed for you, for me, and for, like, the chair sitting in the corner. It's the ultimate neutral referee of reality.
Yeah, we build our entire lives around it.
We really do. Our societies, our sanity, it's all built around that rhythmic certainty. But then you step into the world of theoretical physics and the deep metaphysics of time, and suddenly that ticking clock starts to look like a prop in an elaborate magic trick.
It really is the absolute definition of having the rug pulled out from under your deepest intuitions. I mean, it completely shatters how you see the world.
Yeah, it's wild. We are looking at a fundamental landscape of reality today that is, honestly, completely mind-bending. The physics suggests that time might actually be an illusion. So, welcome to this deep dive. You are joining us for the fourth installment in our four-part foundational series of YouTube clips exploring the core branches of philosophy.
And this is such a crucial one.
It is. Before we can dive into the rich history of philosophy or debate the nuanced ideas of specific thinkers later in the series, we have to establish the core tools and the literal rules of reality. These form the baseline for everything else we're going to talk about. And today's baseline topic is the big one. We're talking about space and time. Specifically, the big question we are wrestling with today is time real?
Which, I mean, that sounds like the kind of question you only ask at 2 in the morning after, like, way too many cups of coffee.
Oh, absolutely.
But it is actually one of the most fiercely debated topics in modern science and philosophy. We just go about our days, ruled by our alarms and calendars, assuming time is this fundamental river flowing from the past through the present and into the future. But the physics we're unpacking today suggests our most visceral intuitions about that river might be, well, completely backwards.
And we have a massive stack of sources to help us figure this out. We are pulling from cutting-edge quantum physics papers, including these wild tabletop Wheeler-DeWitt experiments that we'll get into later, as well as philosophical encyclopedias on the metaphysics of time, cognitive science journals on time perception, and the revolutionary theories of physicists like Julian Barbour and Carlo Rovelli.
It's a lot of material.
It is a lot, but we are going to walk through the mechanisms of how this all actually works together. We're breaking it down.
And the stakes here are incredibly high for how you view your own life. I mean, think about it. If time is an illusion, what does that mean for free will? What does that mean for our memories or, for our loved ones who have passed away? This isn't just abstract math written on a chalkboard. This dictates the very nature of human existence.
Right. It gets really personal really fast. To understand how our view of time is changing, we have to look at how our fundamental understanding of time was broken and then rebuilt by Albert Einstein. But before we get to Einstein breaking it, we need to understand what the classical establishment even was. We need to look at Isaac Newton. But even before Newton, as a bit of a philosophy buff, I want to look at the ancient Greeks.
Oh, yeah, they had a really interesting take on this.
They did, because they actually had a very nuanced dual view of time that I think we've completely lost. They used the word chronos to describe sequential chronological time.
Like the ticking clock.
Exactly, the ticking clock we mentioned. But they also use the word kairos, which refers to the opportune moment, like the psychological or qualitative experience of time.
Right.
Kairos is like when you are waiting for the perfect moment to jump into a game of double dutch, or when a comedian nails the timing of a punchline. It's a moment that's just pregnant with meaning.
And that dual perspective is crucial, because if you fast forward to the 17th century, Isaac Newton comes along and essentially strips kairos out of the scientific picture entirely.
It just deletes it?
Pretty much.
Yeah.
In his 1687 masterwork, The Principia, Newton formalized what philosophers call the substantialist paradigm. He defined time as absolute, true, and mathematical. He viewed space and time as a rigid, unchanging container.
I've always loved that container metaphor. It's like the universe is just this big empty glass box, and within this box, absolute time flows uniformly everywhere, completely independent of the objects moving around inside it.
Right.
Like, if you removed all the stars, all the planets, all the atoms from the universe, Newton argued that space and time would still exist, just ticking away, empty and totally indifferent.
And it's highly intuitive. That is exactly how we experience the world. I mean, the clock on the wall doesn't care if you're sitting still or running on a treadmill. It just ticks. But moving into the 19th century, people started questioning this glass box. A physicist and philosopher named Ernst Mach proposed a radical counter-idea.
Yeah,
He
yeah.
suggested that if all matter disappeared, time itself would actually cease to exist. He argued for relationalism, that time is not a background container, but merely a way of measuring change between physical things. Without things changing relative to one another, time is just a meaningless concept. And this relational philosophy heavily influenced Einstein.
Yeah, Einstein takes Mach's relational ideas and just completely shatters Newton's glass box. With his special theory of relativity in 1905 and general relativity a decade later, Einstein proved that time is not a constant universal river. It is a flexible relative fabric that is intimately intertwined with space. We call it space-time.
Which is a word we throw around a lot, but it's hard to really grasp.
It is. Now, our sources highlight a massive, decades-long physics experiment at Stanford called Gravity Probe B, which points out a huge misconception we have about how this space-time fabric actually works. Because when most people think of Einstein's gravity, they visualize that classic rubber sheet analogy.
Ooh, sure. The bowling ball and the trampoline.
Right. A heavy bowling ball, representing the sun, sits on a trampoline, and a smaller marble, the Earth, rolls around the indentation it makes.
It's the most common visualization of curved space-time in popular science. But the sources point out its severe limitations. That rubber sheet analogy only really helps us visualize the spatial aspect of Einstein's theory. It completely misses the temporal aspect. It misses the actual time and space-time.
Yeah, okay, let's unpack this, because if gravity is just the warping of space, like a marble on a trampoline, why do planets orbit the sun in ellipses rather than just flying off in straight lines? The answer the sources give completely changes how you view the solar system. Planetary trajectories are very nearly straight lines, but they're straight lines in space-time, not just space.
Right. Think of it this way. Earth is moving through space at a certain speed, but it is also constantly moving through time. To understand its true trajectory, you can't picture the Earth as a sphere sitting in one spot.
You have to picture it stretched out.
Exactly. You have to picture a space-time worm. Imagine the Earth's orbit not as a circle, but as a stretched-out, continuous spiral tube. Its width in space is only one astronomical unit, the physical distance from the Earth to the Sun, but its length in the time direction is measured in light years. It's this massive, elongated geometry.
And Gravity Probe B was designed to prove this literal twisting of space-time. They put these incredibly precise, perfect spheres, these gyroscopes, into orbit, cooled to near absolute zero, to see if the Earth's rotation was literally dragging the fabric of space-time around with it.
And it was.
It was. But applying this to our daily experience on Earth brings up something even more profound. So I am sitting in a chair right now. I feel a gravitational pull holding me down. My instinct is that the Earth's mass is warping the space under me. But the sources claim that because our speeds are so small compared to the speed of light and the Earth's gravitational field is relatively weak, nearly all of what I experience as my weight arises from the warping of time, not space.
And that is one of the most difficult concepts in general relativity to internalize. What that means in practice is that a clock on the floor of your room is literally ticking slower than a clock on the ceiling.
Wait.
Because the floor is closer to the center of the Earth's mass. This is gravitational time dilation. Objects naturally follow the path of maximal proper time. In plain English, your body is essentially falling toward the area where time is moving slower. That gradient in the flow of time is what you feel as weight pressing you into your chair.
Okay, hold on. Wait, stop. Are you seriously telling me that my feet are aging at a different rate than my head right now, just because my feet are closer to the floor?
Yes.
That sounds like pure science fiction. How is that physically possible?
I know it sounds absurd, but it has been proven experimentally over and over again with highly sensitive atomic clocks. If you raise an atomic clock just a few dozen centimeters, it ticks faster than the one below it. The physical mechanism is that mass actually stretches the temporal dimension. So if time is moving slower on your floor than on your ceiling, Newton was unequivocally wrong.
The glass box is broken.
Shattered. The universe is not a universal ticking clock. Time is entirely relative to the gravity you are experiencing and the speed at which you are moving.
Man. If my head and my feet are experiencing different rates of time, then the philosophical implication is just staggering. It means we have to completely abandon the concept of absolute simultaneity. There is no universal now.
It has. That is the death blow to the Newtonian container. There is no master clock for the universe. Imagine trying to slice the universe in half with a razor-thin plane and calling that entire slice the present moment, like a universal now spread across the entire cosmos. Einstein showed that such a slice does not exist. What is now for you might be the past for someone else, or the future for a third person, depending on how you are moving relative to one another.
Okay, I understand that if I'm on a spaceship going near the speed of light, my clock runs differently than yours. But if you and I are just walking past each other on the street, our speeds are basically the same. Our nows must be pretty much identical, right? How extreme can this discrepancy actually get in normal, everyday life?
Well, locally, the differences are microscopic. They're practically non-existent.
Mhm.
But the further out you look into space, that tiny microscopic difference in our walking speeds acts like an angle. And over vast cosmic distances, a tiny angle creates a massive sweeping divergence in our nows.
Which leads us directly into a mind-bending philosophical paradox that forces us to question if the future already exists. Our sources dive deep into the Andromeda paradox, formulated by the mathematician Roger Penrose. And I want to really take our time with this because it broke my brain.
That's a tough one.
So imagine two people, Alice and Bob. They are just regular people walking past each other on the street. Alice is walking in the direction of the Andromeda galaxy. Bob is walking in the exact opposite direction, away from Andromeda.
Okay, now Andromeda is about 2.5 million light years away. It is unfathomably distant. Because Alice and Bob are moving in different directions, their hyperplanes of simultaneity, which is the physics term for their individual now slices of the entire universe, are tilted relative to each other.
Because Alice is walking toward it, her now slice is angled slightly differently than Bob's, who is walking away, so they are on a slight diagonal to each other.
Yes. Now imagine an alien civilization in the Andromeda galaxy has just made a momentous decision. They're going to launch a massive space fleet to attack Earth. Because of the 2.5 million light-year distance to Andromeda, that microscopic tilt between Alice and Bob's now slices gets magnified enormously. It's like two laser pointers held right next to each other, angled 1 millimeter apart. By the time those beams hit the moon, they are hundreds of miles apart.
Wow. So how enormously does this time slice diverge at that distance, like practically speaking?
Enough that for Alice, who was walking toward Andromeda, her now slice tilts slightly into Andromeda's future. For her, the alien space fleet launching to attack Earth is an event in her past. The decision has already been made. The ships are physically already on their way.
But for Bob, who is walking away, his slice tilts the other way into Andromeda's past. So for Bob, that exact same launch is in his future. The aliens haven't even made the decision to attack yet. The ships are still on the ground.
Think about the implications of that. Alice and Bob are literally passing each other on the street. They could reach out and shake hands. And yet, for one of them, a cosmic event is a historical fact, and for the other, it hasn't happened yet. And neither of them is wrong. According to the mathematics of relativity, both perspectives are equally valid physical descriptions of reality.
But wait, if a physical event can be in my past but in your future, doesn't that inherently mean the future has to already exist? Because if the alien launch doesn't exist yet for Bob, how can it already be a concrete fact for Alice?
Exactly. And you're hitting on the exact problem philosophers face when trying to build models of reality based on Einstein's physics. Philosophers use reality values to classify these different models. A value of 1 means something is real, it physically exists. A value of 0 means it does not exist. The first model, and the most intuitive to our daily lives, is presentism.
Presentism.
Right.
Presentism says that only the now is real. The past has a reality value of 0 because it's gone. The future has a reality value of 0 because it hasn't happened. And only the present has a reality value of 1. It's like a single frame of a movie illuminated by a projector. Only what is illuminated exists.
Right.
But based on the Andromeda paradox, presentism clashes deeply with relativity. If Alice's now is completely different from Bob's now, whose now is the real one, presentism demands a universal present, which we just established Einstein completely destroyed.
Which forces many physicists and philosophers into the second, much heavier model, which is eternalism. It's widely known as the block universe. What's fascinating here is that in eternalism, the past, the present, and the future all exist equally. They all have a reality value of 1. The universe is a four-dimensional static block of space-time. Every event, from the Big Bang to the heat death of the universe, including your birth and your ultimate death, is equally real and permanently fixed at specific coordinates in this block.
So, to use the movie reel metaphor, the whole movie, beginning, middle, and end, exists simultaneously on the physical reel of film. The frames at the end of the movie exist just as tangibly as the frames at the beginning. You, as the viewer, are only experiencing it one frame at a time.
Exactly.
The frame you are watching is your localized now, the frames you've seen are your past, and the frames still on the reel are your future. But the reel itself is a single, complete object.
Eternalism turns time into a landscape. Just as here's an indexical word pointing to your spatial location, like here's a studio for you, but here's a coffee shop for someone else listening now, is just an indexical word for your temporal location. Now, isn't a magical, glowing property of the universe? It just means the specific time coordinate at which I am currently speaking.
And the sources point out that this leads to two completely different views on how humans actually exist through time. Endurantism versus perdurantism. Endurantism is the classic view. You are a 3D object, wholly present right now, and you endure through time. You move through the container. But eternalism leans heavily toward perdurantism. Perdurantism is the idea that we don't endure through time. We are actually 4D objects. We have temporal parts.
Yes. Just as you have a left arm and a right arm, which are spatial parts of you, you also have temporal parts. There's a child part of you, an adult part of you, and an elderly part of you. You are a space-time worm, just like the Earth's orbit we discussed earlier. And all those temporal parts of you exist simultaneously, stretched out like a long, fleshy cable embedded in the block of space-time.
Okay, I have to stop you there. That is profoundly alien to how human beings feel. If my elderly part is already sitting at some coordinate in the block universe permanently fixed, then my entire life is pre-written. Doesn't the block universe completely destroy free will? Our sources mention the classical Rita-Putnam argument from the 1960s, which argued exactly that relativity implies fatalism. If the future is out there, I can't change it.
It's definitely the most common existential fear regarding the block universe. But many philosophers argue that eternalism does not destroy free will. The philosopher Christy Miller, cited in the sources, makes a very delicate but crucial distinction. Just because the future is fixed doesn't mean your choices don't causally create that future.
I'm struggling to see the difference. How can a fixed future be created by my free choice? If it's already there, my choice is an illusion.
Think of it this way. The block universe is the total sum of all causes and all effects. Your conscious choices are the actual causal mechanisms that determine the shape of the block. If it is true that you're going to eat a sandwich for lunch tomorrow, that future event exists in the block because of the choice you'll make to make a sandwich.
Oh, I see.
The future is fixed because of your choices, not in spite of them. From a hypothetical God's eye view outside the 4D block, your choices and their consequences are visible all at once. But inside the block, the causal chain, your agency, your deliberation, your action, is the very real engine connecting point A to point B.
So it's not that I'm trapped in a cart on a pre-built roller coaster track. It's that I am the one actively laying down the track in front of me. But from a four-dimensional perspective, the entire track from start to finish just looks like a single solid piece of geometry.
That is a phenomenal way to visualize it. But it is still a bitter pill for many to swallow, which is why there is a third major model called the growing block theory, or the crystallizing block, heavily promoted by cosmologists like George F.R. Ellis. The growing block theory tries to compromise. It says that the past and the present exist. They have a reality value of 1, but the future is 0. It's an open, probabilistic void. As the present moves forward, quantum wave functions collapse, and the fluid probabilities of the future crystallize into the solid, fixed block of the past.
It's a highly dynamic view, and it comforts us because it conforms to our common sense intuition that the past is unchangeable and the future is unwritten. Ellis argues that events deep in the past continually structure the present moment, like how nuclear reactions in stars billions of years ago produced the literal carbon atoms in our bodies today. The past is real and heavy. But our sources also detail a devastating philosophical critique of the growing block theory from a philosopher named David Braden Mitchell. And this critique completely shattered my comfort with the growing block idea.
Oh yeah, Braden Mitchell's critique is brilliant. He attacks the epistemic foundation of the theory.
He asks a terrifying question. He says, if the past is a solid block and the present is just the razor-thin growing edge of that block, how do I know I'm actually on the edge? Think about it. Socrates thought he was in the present when he was debating in ancient Greece. He felt the sunshine. He felt the passage of time. According to the growing block theory, Socrates' past is real, but his present crystallized into the block thousands of years ago. So what if we are just a frozen slice of the past? What if the true growing edge of the universe is millions of years ahead of us, and we are just experiencing the illusion of now because our specific temporal slice happens to contain the memory of yesterday?
It's a profound epistemic trap. If the past is ontologically real but dead and inactive, you have absolutely no way of proving you aren't inhabiting the dead past right now. The feeling of now would be identical whether you were on the growing edge or buried deep in the crystallized center. This dizzying logic is why some thinkers propose a fourth model, existential realism.
Right. Existential realism tries to find a pragmatic middle path. It distinguishes between existence, which it defines as the present, observable, active state of being, and reality, which includes the structural, causal weight of the past and future. It preserves the empirical primacy of the present moment without demanding that the past and future literally exist in the exact same physical way your coffee cup exists right now.
It's an earnest attempt to anchor philosophy in our human experiential reality while still honoring the physics of relativity.
Okay, let's recap where we are. So Einstein gives us a flexible fabric of space-time on a cosmic scale, and philosophers give us a frozen 4D block. But if we take a microscope and zoom all the way down into the atomic fabric of that block, does the block hold up? Because everything we know about quantum mechanics suggests it shouldn't. When we look at the subatomic quantum level, the concept of time doesn't just freeze into a block, it disappears entirely.
Yeah, we're touching on one of the greatest crises in modern physics. For nearly a century, physics has rested on two massive, incredibly successful pillars: general relativity, which handles gravity and the very large, and quantum mechanics, which handles the very small. The problem is they hate each other.
They really do.
They speak completely different mathematical languages, and the most glaring contradiction between them is how they treat time. In general relativity, as we've spent the last 20 minutes discussing, time is a dynamic, malleable dimension of space-time. It bends, it stretches, it dilates. But in standard quantum mechanics, time is treated as an absolute external background parameter. It's the ticking metronome outside the experiment. It doesn't bend.
So physicists have been desperately trying to unify them into a single cohesive theory of quantum gravity. And in the 1960s, two physicists, John Wheeler and Bryce DeWitt, managed to write down an equation that attempted to apply quantum mechanics not just to a single atom, but to the entire universe as a whole. This is the famous Wheeler-DeWitt equation.
And when they wrote it down and solved the math, something shocking happened. In a standard quantum equation, you always have a variable for time. It describes how a wave function evolves, how a system changes over time. But when Wheeler and DeWitt combined the math of the cosmos with the math of the quantum, the time variable literally canceled out. It vanished.
I mean, in physics terms, the Hamiltonian operator, which measures the total energy of a system and dictates how that system changes, just equals zero. Instead of a formula evolving over time, the entire energy equation zeroes out.
This is widely known in physics as the frozen formalism. According to the math, the wave function of the universe does not evolve. The universe, fundamentally at the deepest quantum level, is entirely static. There is no time.
As a philosophy guy, this immediately sounds exactly like Parmenides, the ancient Greek philosopher who argued that change is a complete illusion, and reality is a singular, unchanging whole. Parmenides said that motion was impossible.
It is the ultimate mathematical vindication of Parmenides. But it leaves modern physicists with a massive problem, which they quite literally call the problem of time. If the fundamental equation of the universe says reality is completely static, how do we explain the undeniable fact that things are clearly moving, changing, and evolving right in front of our eyes?
Right. Enter the physicist Julian Barbour. He is a prominent, somewhat radical independent researcher who essentially looked at the Wheeler-DeWitt equation and said, I believe it, the math is right, time doesn't exist. In his 1999 book, The End of Time, he proposes a massive paradigm shift. He goes back to Ernst Mach, the guy who influenced Einstein. Barbour argues that time doesn't exist in the background. Rather, we infer time by comparing changes in relationships between objects.
Barbour says we should stop thinking about a container of space and time and instead think about what he calls shape space. He calls this mathematical arena Platonia. Let's visualize this. Imagine you have a cosmic tool table and you dump a bunch of billiard balls onto it. They scatter and come to rest. That specific exact arrangement of balls is a shape or a configuration.
Okay, I'm picturing it. And Barbour argues that the universe is just an infinite collection of these instantaneous 3D configurations. He calls these static snapshots nows. Every possible arrangement of the atoms in the universe exists as a static, unmoving point in Platonia. Here's where it gets really interesting. It's like an infinite pile of photographs scattered on a floor. The universe doesn't flow through time. It's just a vast, static archive of these nows.
Barbour is taking relationalism to its absolute logical extreme. The universe doesn't have a time dimension. It just has structure.
Okay, but this is where I have to heavily push back. If reality is just an unorganized pile of static, disconnected photographs, why do I experience a seamless, ordered narrative of history? If you are telling me my childhood still exists as a static snapshot somewhere in Platonia, why do I remember yesterday, but I don't remember tomorrow? How do we get from one snapshot to another?
You are hitting on the exact crux of Barbour's theory. Barbour answers this with a brilliant concept he calls time capsules. He points out that certain nows, certain snapshots in the pile, have highly correlated structures built right into them. Think of a dinosaur fossil buried in a layer of rock, where the sedimentary layers in the Grand Canyon, or, most importantly, the memory engrams stored in the neurological pathways of your brain.
They are static physical arrangements that heavily imply a history.
Exactly. A fossil isn't actually the past. A fossil is a specific arrangement of calcium and rock existing right now, but its structure is so complex and highly correlated that it mathematically points toward other specific nows in Platonia, the snapshots where the dinosaur was alive. Our brains, which are themselves highly complex, correlated physical structures, essentially hop between these closely related nows. We interpret these static structural records as a flowing history, creating the psychological illusion of motion and causality.
So my entire sense of motion, my memory of waking up this morning, my anticipation of having lunch later, it could all be a cosmic optical illusion. It's just my consciousness finding a statistical path through highly correlated, entirely static nows.
According to Barbour's strong claim, yes, there is no time, only nows, and our entire sense of history is fully explained by the existence of record-like structures inside certain nows.
That is deeply unsettling. But it also feels like we are missing a mechanical engine. If everything is just static shapes, how does a timeless universe generate the actual physical feeling of a ticking clock? To explain how a timeless universe generates the illusion of change, we have to look at two massive breakthroughs in modern physics: quantum entanglement and the arrow of entropy. Let's start with quantum entanglement. If the Wheeler-DeWitt equation says the universe is static, how does the clock on my wall tick? In the 1980s, physicists Zahn Page and William Wooters proposed a mechanism that blew my mind.
The Page-Wooters mechanism.
Yeah.
It is one of the most elegant solutions to the problem of time. They suggested that time emerges purely as a byproduct of quantum entanglement. The idea is that if you look at the entire universe from the outside, a hypothetical God's eye view, it is completely static, perfectly satisfying the Wheeler-DeWitt equation.
Right.
If you are inside the universe, your perspective changes entirely.
The sources use a great analogy for this. It's like looking at a snow globe. From the outside, the globe just sits on the shelf. It's a static, unmoving object. But if you were a tiny, microscopic person inside the water of the snow globe, entangled with the swirling flakes, you would perceive a dynamic, changing environment.
Page and Wooters realized that by mathematically partitioning the universe into subsystems, time suddenly appears. Let's say one subsystem acts as a clock, and the other subsystem is the observer. Because the observer and the clock are quantumly entangled, when the observer measures the clock, they get a specific state. When they measure the rest of the universe relative to that clock state, it looks different. A sequence of changes appears. Because they are entangled, the observer perceives the universe evolving relative to that internal clock, even though the global system remains at zero energy.
And this isn't just abstract math on a chalkboard anymore. Our sources cite a jaw-dropping recent paper detailing a literal tabletop Wheeler-DeWitt universe experiment. Researchers actually created a mini-universe in the lab to test this.
Yes. They set up a quantum system using entangled photon pairs that, as a whole, was completely static. Its global Hamiltonian was exactly zero. The mini-universe was frozen.
But then they partitioned this mini-universe. They used the polarization of one photon as the clock sector and the other photon as the system sector. And when they observed the system from the perspective of the clock photon, they literally watched an entropic time emerge. The system appeared to evolve purely based on the quantum entanglement between the sectors.
If we connect this to the bigger picture, the paradigm shift here cannot be overstated. What this proves is that time is not a fundamental ingredient of the universe. It is not built into the basement of reality like mass or electric charge or spatial dimensions. Time is an emergent property.
The best analogy for an emergent property is temperature. A single isolated helium atom does not have a temperature. Temperature doesn't exist at that scale. Temperature is just the emergent average kinetic energy of a large group of atoms bouncing around and hitting each other. You need the group relationship for temperature to exist.
Precisely. Similarly, a single global quantum state doesn't have time. Time emerges only when you split the system into entangled subsystems. Time is a relationship.
But that only brings us to the second half of the puzzle. The Page-Wooders mechanism explains how a ticking clock can emerge from a static state, but it doesn't explain the direction of the ticking. Why does the clock only tick forward and never backward? Why does the egg break on the floor, but the yolk never spontaneously leaps back up into a perfect shell?
Right, the famous arrow of time. And for that, we have to talk about thermodynamics, specifically the second law, which governs entropy. Entropy is broadly understood as the measure of disorder, or, more accurately, the number of possible microscopic configurations a system can have. The second law of thermodynamics states that in a closed system, entropy always tends to increase. Heat naturally flows from hot to cold. Ordered structures inevitably decay. A dropped egg splatters.
And because there are billions of ways for an egg to be splattered and broken, but only one incredibly specific way for an egg to be perfectly whole, it is statistically vastly more probable for a system to move from order to disorder. You never see a splattered egg spontaneously reassemble itself, because the statistical odds are infinitesimally small. This thermodynamic gradient, the steady, inescapable march from low entropy to high entropy, is what gives time its one-way arrow.
Think of it like a massive panorama photograph. The photograph itself is a static object. It doesn't possess time. But imagine the left side of the photo is perfectly white, and it gradually fades into pitch black on the right side. That gradient of light to dark creates a directional narrative across the static image. Entropy is the physical gradient that gives our static universe a directional arrow.
But cosmologists have long struggled with a massive headache regarding this gradient. For entropy to be constantly increasing today, the universe must have started in a state of incredibly, almost miraculously low entropy at the Big Bang. It's like finding a perfectly ordered deck of cards. Why was the initial state of the universe so highly ordered?
Julian Barbour, our shape space guy from earlier, steps back into the arena here with his recent work, the Janus point. He wants to rebut the idea that the universe just randomly, luckily, started with arbitrarily low entropy. Barbour opposes that the Big Bang was not a magical singularity of low entropy, but rather a Janus point of minimal complexity. He measures this complexity with a term he coined called exinity, how distinctly a shape stands out against uniform simplicity.
And like the Roman god Janus, who has two faces looking in opposite directions, Barbour argues that time branches out from the Big Bang in two opposite directions. From this central point of minimal complexity, the universe expands, and structural complexity grows outward in both directions. Wait, if time branches in two directions from the Big Bang, are you saying, is there an entire other side of the universe moving backward? Like a literal anti-universe on the other side of the Big Bang?
Conceptually, yes. If Barbour's model holds, there is a mirror universe extending from the Big Bang, where time flows in the exact opposite direction relative to us. Though anyone living in that universe wouldn't feel like they were walking backward. They would feel like time is moving forward, just as we do, because their psychological arrow of time would perfectly align with their local thermodynamic arrow of entropy.
That is staggering. A mirror reality where our past is their future. And this leads perfectly into the revolutionary theories of physicist Carlo Rovelli. Rovelli takes all of this, the timeless quantum mechanics, the relational entanglement, the thermodynamics of entropy, and synthesizes it into his thermal time hypothesis.
Rovelli is one of the founders of loop quantum gravity, and he strongly advocates that at the microscopic scale, reality is made of processes, not things. But crucially, these processes do not happen in time. Time is not the background.
Rovelli argues that time is purely a macroscopic thermodynamic effect. In a timeless universe, we use states in thermal equilibrium to define a physical time parameter. Time is quite literally the physical manifestation of our ignorance of the microstates of the universe. Because we are large, clumsy biological creatures, we can't see the individual quantum states of every atom, so we experience the macroscopic statistical blurring of entropy, which we call time.
It's all about perspective.
Okay, I have a major fundamental pushback here. Physicists are telling me that time is a thermodynamic optical illusion. It's an emergent property of quantum entanglement and statistical blurring. But I feel the flow of time right now. I feel the anxiety of a deadline approaching. I feel the physical relief when an hour of heavy traffic is finally over. If time is just a structural gradient in a static block or a statistical blur of ignorant atoms, why does it feel so incredibly real, so dynamic, and so fluid to my human brain?
That is the ultimate question. Physics can tell us about the block, but physics cannot tell us about the flow. To answer that, we have to leave the realm of astrophysics and quantum mechanics entirely. We must look at neuroscience and cognitive psychology to understand why we feel the flow.
Let's start with a brilliant concept from the pioneering psychologist William James. Over a century ago, he coined the term the specious present. When we think of the present, we usually think of a razor-thin mathematical instant, a durationless point between the past and the future. But James argued through observation that human consciousness doesn't operate like that at all. The present we actually experience is not a point, it is an interval.
Our sources from modern cognitive science back this up beautifully. The specious present spans roughly 3 to 5 seconds. Think about when you listen to a melody. You aren't just hearing a sequence of isolated, durationless, disconnected notes. You are experiencing the current note while actively holding the reverberation of the previous notes in your immediate awareness and simultaneously anticipating the next note. It's a sliding window of perception.
Cognitive scientists call this the immediate present train, or IPT. Human consciousness stitches together these discrete episodes of experiencing these 3 to 5 second intervals into a phenomenal continuous flow. It's remarkably similar to how a movie projector stitches together 24 static frames per second to create the illusion of perfectly smooth motion.
And the physical neurology behind this is fascinating. Your brain is essentially a biological sampling machine. It samples the sensory environment at a rate of roughly 5 to 10 hertz. Every 100 to 200 milliseconds, your brain takes a snapshot of your visual and auditory inputs.
But here is the critical link back to the physics we just discussed. Recording these sensory snapshots, laying down these physical memories in our neural pathways, requires metabolic energy. Your brain burns calories to make a memory.
And consuming metabolic energy generates heat, which increases the total entropy of the universe.
This binds our psychological arrow of time directly to the physical thermodynamic arrow of time. Our brains can only record memories in the direction of increasing entropy. We remember the past, but not the future, because the physical act of recording the memory increased the entropy of the present.
Synthesizing this, we can definitively say that our brains evolved to survive in a universe governed by thermodynamics. Our subjective experience of a flowing river of time is not a delusion. It is a highly sophisticated, evolutionary cognitive tool constructed by the brain. It is a biological user interface that allows us to navigate a universe of static, highly correlated quantum snapshots.
Viewing time as a cognitive construction explains so many of our everyday temporal illusions. Have you ever noticed why time flies when you're having fun, but a single day stuck in a sterile waiting room feels like a decade? It comes down to novelty versus familiarity in cognitive processing.
When you are in a novel, exciting situation, your brain is processing vast amounts of new information, but it groups it efficiently into dense memory chunks. When you look back, the interval feels incredibly compressed because the data was packed so tightly. But in a waiting room, your brain is starved for novel input. It has nothing to process. So it focuses on the passage of time itself, laying down more frequent empty timestamps in your memory, making the duration feel agonizingly long.
Our sources compare the mind's construction of time to well-known sensory illusions. Take the color 5 phenomenon. If you flash a red dot on the left side of a screen and a split second later flash a green dot on the right side, your brain doesn't just see two separate static flashes, it actually constructs an image of a single dot moving across the screen and magically changing color halfway.
Which proves your brain is actively predicting, hallucinating, and filling in the gaps of reality to create a smooth, continuous narrative out of discrete static sensory inputs. Or consider the finger sausage illusion. If you point your two index fingers at each other, leaving a tiny gap, and hold them close to your eyes, your brain merges the images to create a weird floating sausage between them. The sausage does not physically exist. It's a constructed reality.
Just like the flowing river of time. Which leads to a fascinating, almost sci-fi speculation. If human perception dictates the flow based on our specific 5 to 10 hertz biological sampling rate, do different biological organisms inhabit literally different temporal realities? A housefly has a much faster visual flicker fusion rate than we do. It samples the world much faster. That's why it's so hard to swat a fly. To a fly's brain, your hand is moving in slow motion. Conversely, a tortoise might sample the world much slower. They're quite literally living in completely different timescales.
It truly emphasizes that time, as we experience it, is a biological interface, not an objective cosmic property.
So what does this all mean? We started with a ticking clock in a quiet room, and we've completely dismantled it. We've replaced it with a frozen block, quantum entanglement, entropy, and brain hallucinations. Does calling time an illusion demean our human experience? Does it make our daily lives, our struggles, our waiting rooms less meaningful?
I would argue the exact opposite, realizing that time is not an external, indifferent dictator, but a relational, emergent property intimately constructed by our own consciousness, places humanity right at the center of the mystery. It suggests that our consciousness is one of the most powerful forces in the universe. We are the literal engines that turn a frozen quantum reality into a flowing, lived experience.
Let's recap this epic journey. We started with Isaac Newton's rigid, absolute glass box of a universe where time ticked uniformly everywhere. Then Einstein broke the box, showing us that space-time is a flexible fabric, where gravity is literally the warping of time, and absolute now is a mathematical fiction.
Then we plunged into the heavy metaphysics of the block universe, wrestling with the Andromeda paradox, and the realization that the past, present, and future might all exist simultaneously in a massive 4D landscape.
We dove even deeper into the quantum depths, looking at the frozen formalism of the Wheeler-DeWitt equation, where the math says time disappears entirely, leaving us with Julian Barbour's Platonia, an infinite realm of static nows connected only by structural fossils.
We found our way back to motion through the Page-Withers mechanism, seeing time emerge relationally through quantum entanglement, given a forward direction by the relentless thermodynamic march of entropy and the second law.
And finally, we arrived at the human brain, biological machines sampling the universe at 10 hertz, burning metabolic calories to stitch static snapshots into the beautiful, flowing, specious present. Understanding that time is relational and emergent frees us from the anxiety of a ticking cosmic clock. It reminds us that the present moment, the 3 to 5 second interval you are experiencing right now, is where your existence physically resides. It is the only place where you can exercise your agency to shape the track of the 4D block. And that leads me to one final provocative thought for you to mull over as we wrap up today's deep dive. We've talked a lot about the block universe, about eternalism, about how relativity implies that the past still permanently exists. If eternalism is true and every moment of your life from your birth to your last breath already exists as a permanent, indelible coordinate in the 4D block of space-time, then nothing is ever truly lost. Your most cherished memories, your childhood home exactly as it was, the loved ones who are no longer sitting beside you, they aren't fading away into some dark, dead past. They're still happening, permanently etched in their specific space-time coordinates. You just happen to have walked slightly further down the block. If time is an illusion, perhaps loss is an illusion too.
That is a profoundly beautiful way to look at the physics. The universe isn't deleting the tape behind us. It's just that our biological spotlight of consciousness has moved to a new coordinate.
So the next time you sit in a quiet room and hear a clock ticking, I hope you don't just hear the passage of an absolute law. I hope you hear the sound of your own brain entangled with the universe, actively constructing the flow of reality second by second. Thank you for joining us for this foundational exploration. We've established the rules of space and time. Join us next time as we continue our philosophy series and dive into the next foundational pillar of reality. Until then, stay curious.